Welcome to the Getting Started with GeoStudio video series. This tutorial video will discuss how to fine-tune the mesh using the finite element meshing options in GeoStudio products. This tutorial video will also explain how to remove mesh constraints from the finite element mesh. A summary of practical guidelines for good meshing practice is also outlined in the product-specific engineering books. It is recommended that these chapters are also reviewed for the user's specific product of interest. Let's start by looking at a two-dimensional steady-state model in the SeepW product. Here we can see the model domain consists of an embankment with a reservoir level of 11 meters on the upstream side of the embankment. There is currently also a drain along the downstream side of the embankment below the toe, and two lines representing a potential core material in the middle of the embankment. We will first turn on our current mesh by going to View, Preferences. In this window, we can turn on and off many of the visualization parameters, but we will simply turn on the mesh. Now we can see how our current mesh looks with no constraints added. Next, we will open the Mesh Properties window by going to Draw Mesh Properties. We can see that the current global element size is set to 1 meter. This element size has been drawn by default and can be modified to alter the size of the elements at a global level for the entire mesh. Generally, it is recommended that the mesh is not altered too much, and only necessary alterations should be made at a few limited locations where finer or coarser discretization is needed. First, we will look at the different finite element mesh pattern options available in the GeoStudio products. Each of the products currently allows automatic mesh patterns to be created based on an unstructured mesh type. The unstructured meshing pattern will generate a well-behaved pattern of either a mixed quadrilateral and triangular element pattern or a triangular element pattern. The triangular mesh pattern can be used if the user prefers a mesh that is automatically created using the Delaunay triangulation techniques. The unstructured mesh type is recommended as the algorithm creates a well-behaved pattern, especially for odd-shaped regions. There are also two structured mesh option types available. The first is the triangular grid of quads and triangles and has been included for triangular regions. This meshing type creates a mix of square, rectangle, trapezoid, and triangle elements. The second structured mesh uses a rectangular grid of quad elements and is only recommended for rectangular regions. If used on other regions, this mesh type can be more difficult to control. In our SeepW example, we will simply keep the quads and triangles unstructured mesh. We will also keep the default global element size of 1 meter. Given the drain under the toe of the embankment, we know that there will be a phreatic zone located somewhere along this line. To ensure that we have a more accurate representation on the location of this phreatic zone, we will change the mesh discretization along this line to 0.5 meters. To do this, we will click on the line representing the drain and choose the ratio of default size option from the drop-down menu. By entering 0.5 for our ratio, this creates element sizes of 0.5 meters along the line. The global mesh automatically adapts the quad and triangle elements to accommodate this constraint. The other option would have been to simply choose the length of option and enter in the 0.5 meter constraint. The number of divisions option defines the number of elements the user desires along the line or edge. In this case, to obtain the desired 0.5 meter element size, we would simply use the line length, which is 7 meters, and divide the length by 0.5, giving us 14 divisions along the line. Now, let's assume we have a geofabric located along a line in our embankment. Interface elements are an option in some of the GeoStudio products and are given specific material properties using the Key in Materials window. These interface elements can be used for creating geofabric materials or no-flow barriers in SeepW, thin insulation layers in TempW, or to assign friction properties between soils or between a soil and a structure in SigmaW. There are two methods that can be used to create interface elements. The first method is to create the material in the Key in Materials window that will represent the geofabric or no-flow barrier. Then, when I use Draw Materials, I can choose the line option and click on the location that I wish to simulate my barrier. This will automatically create my interface elements. Now, when I return to the Draw Mesh Properties window, I can choose the line again and see that there are interface elements with a thickness of 0.2 meters. We can zoom in closer to see the barrier material color, which is green, is applied only to the interface elements along one side of the line. It is important to note that you cannot remove interface elements from a mesh if there are material properties still applied to them. In order to remove the interface elements, we must go to Draw Materials, click on Remove from Lines, and remove the barrier material from the interface elements. Now we can return to the Draw Mesh Properties window and remove the interface elements. To add the elements from the Draw Mesh Properties window, you can simply highlight the line and click on the Generate Interface Elements toggle and define the desired thickness. Lastly, we will take a look at secondary node options in the Draw Mesh Properties window. The number of sample or integration points required in an element depends on the number of nodes and element shape. For example, a triangular element that has a one-point integration results in a constant gradient throughout the element. When secondary nodes are present, however, the interpolating functions are nonlinear and require a higher integration order. The table shows acceptable integration orders for GeoStudio products. For quadrilateral elements, there is the option of 4 or 9-point integration with elements with or without secondary nodes. In this case, however, the benefits are marginal and higher computing efforts are required when 9-point integration is used. Generally, the use of 3-point integration for triangular elements and 4-point integration for quadrilateral elements is sufficient for most simulations. Secondary nodes are typically used in stress-strain analyses. If, at any time, the user wants to restart the fine-tuning of the mesh or decrease complexity, the Remove Constraints button can be used to return to the global element size with no mesh constraints or discretization. Remember, interface elements must not have materials applied to them prior to removal, or else the interface elements will remain within the mesh. To summarize this video tutorial, there are two meshing types available: structured, and unstructured. It is recommended that the unstructured mesh is used for most simulations, especially those with odd-shaped regions. Interface elements can be used for simulating thin materials along lines within the domain, such as geofabrics, thin insulating layers, or for material behavior, such as friction behavior between a soil and a structure. Remember, to remove interface elements, you must first remove the materials that are assigned to the lines representing these thin materials, and then return to the Draw Mesh Properties window to toggle off the interface elements. Lastly, secondary nodes and integration orders can be used to increase the performance of the model. It is recommended that the 3-point integration is used for triangular elements, and 4-point integration is used for quadrilateral elements. Secondary nodes are often used in stress-strain analyses. It is recommended that the user starts with a mesh that is less than 1,000 elements at the start of an analysis. Once a good understanding has been developed on the critical mechanisms in the particular problem that is being simulated, the user can increase the discretization of the mesh as required. If too many elements are used initially, the solution can take a long time to compute, or may become unattainable, or results may become difficult to interpret. Remember, it is better to keep the problem as simple as possible first, and then increase complexity only as necessary as the main engineering issues become well understood. We have now reached the end of this tutorial. Note that not all of the powerful features of version 9 of GeoStudio have been used or discussed here. Further information on each command can be found in the online help, supporting documentation, as well as in other tutorial videos. Thank you for watching.